In this lesson, we shall focus on grade 10, physical sciences, and in particular, we shall focus on the chemistry paper, paper 2, written in 2 hours out of 150 marks. It was written in the year 2018 in November, and we discuss the questions and associated solutions to the questions as follows. Right, question 1 is actually a multiple choice set of questions, or in question 1, we are focusing on multiple choice questions. Various options are provided as possible answers to the following questions. Each question has only one correct answer. Choose the answer and write only the letter A to D next to the question numbers 1.1 to 1.10 in the answer book. E.g., right, in 1.11, you can just say the answer is the letter D. That's all. Right, so in 1.1, here are the questions. Right, which one of the following substances is not a pure substance? Is it iron? Is it sugar? Is it steel? Is it graphite? Which one do you think is the correct answer? Anyone home? Which one is not pure? It is not a pure substance. So it is a mixture of different substances. Which one? Which one do you think is actually a mixture of substances and therefore is not a pure substance?
B or D?
Okay, that's fine. That's fine. That's fine. So the correct answer is the letter C. Right, the correct answer is the letter C for steel, because we know very well that steel is an alloy. Steel is an alloy, and therefore steel combines different metals. Okay, so steel itself is not a pure substance. Okay, so that is the answer to 1.1. Next question. The correct chemical formula for potassium nitrate is which one? There's something we call potassium nitrate, and which one is the correct chemical formula for potassium nitrate? Which one? Anyone? Right, so the correct answer is this one here, and this is the correct chemical formula for potassium nitrate. It is actually KNO3, and this is called potassium nitrate, and that is the correct chemical formula. 1.3. Different isotopes of the same element have different what? Different isotopes of the same element have different what? What do you think here? Anyone home? Anyone home?
Kana meaning definition
I'm just testing you. Yeah, what do you think? Different. Okay, we're speaking about different isotopes. Okay, of the same element have different what? Okay, so at this point, obviously we are learning. And okay, yeah, yeah. Well done, well done. You're really smart. Give B. So different isotopes of the same element have different numbers of neutrons. Different numbers of neutrons. So different isotopes of the same element have different what? Numbers of neutrons. Okay, so we continue. We then continue. Right, next question. Right, so this question here, we can most certainly, we actually in 1.4, we need to ignore this question. So we shall ignore this question. It had issues. So we ignore this particular question 1.4 and move to the next one. Right, 1.5, which pair of elements is most likely to have a similar arrangement of outer electrons and similar chemical behavior? Right, so we're looking at a pair of elements which is most likely to have similar arrangement of outer electrons and similar chemical behavior. Is it boron and aluminium, helium and fluorine, carbon and nitrogen, chlorine and oxygen? Which one, which pair of elements is most likely to have similar arrangement of outer electrons and similar chemical behavior? Similar chemical behavior. Right, obviously in view of the periodic table, it is very clear that it is option A that such that you have boron and aluminium. Boron and aluminium are actually likely to have the similar arrangement of outer electrons and similar chemical behavior. The rest are very, very different from each other. The rest are very different from each other. For example, I mean, indeed, they cannot have the same chemical behavior because chlorine is what? Chlorine is a halogen. Chlorine, fluorine, bromine, all those are halogens. So now here is a halogen and here's another. So B and D can't be because these are halogens and oxygen is not a halogen. So if we speak about similar chemical behavior, therefore obviously these are odd because the combination of a halogen and oxygen. Now your carbon and nitrogen are out, and therefore those with a similar chemical behavior will have to be boron and aluminium then. Next point. Right, in 1.6, we're saying which one of the following statements is incorrect? Which one is incorrect about the properties of a physical change? When a physical change occurs, the compounds may rearrange themselves. Right, when a physical change occurs, the compounds may rearrange themselves, but the bonds in between the atoms will not break. Right, next we are looking at physical change in matter is reversible. Energy is absorbed when matter changes from a solid to a liquid. Molecules are not conserved during a physical change. Now look at these very carefully. Welcome, Nombuso. Right, so yeah, this one is grade 10. We are welcome to participate in the grade 10 discussion, but we will most certainly have grade 12 tomorrow at the same time. So yeah, but this is grade 10, but we are welcome to participate in the grade 10 discussion. So which one of the following statements is incorrect about the properties of a physical change, right? So yeah, you're welcome to participate, numbers, but this is actually it's grade 10 today, okay? And then tomorrow is gonna be grade 12 at 20 hours to 22 hours. It's gonna be, there's gonna be lots of science for grade 12. So you encouraged to join us there, okay? Because we're gonna be looking at the June exam preparations. Now at this point, which one of the following statements is incorrect about the properties of a physical change? When a physical change occurs, what is physical change? Physical change, I mean, there can be a change from solid to liquid or to a gas. So when a physical change occurs, the compounds may rearrange themselves, but the bonds in between the atoms will not break. Okay? Physical change in matter is reversible. Which one is wrong? Which one is incorrect? Energy is absorbed when matter changes from a solid to a liquid. So when ice changes to water, is energy absorbed or not? Think about this, okay? Molecules are not conserved during a physical change. So you see, the question we're then asking is which one is the correct answer here? So the correct answer here is that molecules are not conserved during a physical change. And obviously this is wrong. It is therefore the incorrect option. It is incorrect to say molecules are not conserved during a physical change, because when a physical change happens, somebody takes a block of ice, and here's a block of ice, and it is converted to water. You take ice, an ice block, and it's converted to water. The truth is the molecules are conserved. It's still water, but the water is it's ice. But now the same water becomes a liquid. Okay, so look at the fact that the water here is a solid, because ice itself is a solid, but now the molecules themselves are not conserved during the physical change. It is not correct. So molecules are conserved, because as much as the water changes its state, so water can be a solid, it can be a liquid, but also water can evaporate and form clouds and become water vapor. In which case, according to science, it is therefore very clear that the molecules themselves are conserved. Take note of that. So yeah, it is incorrect because we had to look for the incorrect one. The rest are correct. To say energy is absorbed when matter changes from a solid to a liquid. So indeed, energy is absorbed when this is correct, because what would it mean to say energy is absorbed when matter changes from a solid to a liquid? We understand that when matter, like with ice, the example of ice that changes to water, it's still water, whether it's water vapor or whether it's an ice block. But it's so if therefore matter changes from a solid to a liquid, we understand therefore that to mean the following, to actually tell us that energy is absorbed. The heat is what would change like solid water to liquid water. Okay, yeah. And the physical change in matter is reversible. So yeah, it is true to say physical change in matter is reversible. Okay, yeah, you can change, is reversible. So you can change water from ice to liquid. But also if you have liquid water, you can refrigerate it. You can freeze water to ice, back to ice. So this is just reversible, which is a physical change. Next. 1.7, in the compound H2O. Right, we are looking at the compound H2O. The ratio of the mass of hydrogen to oxygen is always what? We're looking at the ratio of hydrogen to oxygen. The ratio of hydrogen to oxygen is what? Is it 1:2? Is it 2:1? Is it 1:8? Is it 1:16? The ratio of the mass. The ratio of the mass is what? Anyone home? Right. Anyone home? Right, who knows the ratio of the mass is what? You forgot this one. What? Okay, what is the mass of hydrogen? What is the molecular mass of hydrogen? Okay, I'm going to show you. I know that you know these things, but you forget. Okay, there's something I want to show you now. It is at the back. So we speak about the molecular mass of hydrogen and that of oxygen. Okay. Never mind that. So, right, we're speaking about the molecular mass of hydrogen and that of oxygen. And I want to show you something. There's something I'm going to show you just in 1 second. Right, I want to discuss with you the periodic table of the elements that we study in chemistry grade 10. Take a look. Okay, let's look at hydrogen and look at oxygen. Here is hydrogen and there is oxygen. Right, so what is the ratio of the mass? So we can see from the key here. Here's the key. The key is that we have the appropriate relative atomic mass, like the atomic mass of copper is 63.5. Okay, that of hydrogen is 1, and that of oxygen, we can see the relative atomic mass is what? Is 16. But obviously, I mean, then what then do we do at this point? What then do we do at this point? So we saw 1 and 16. Let's use that here to answer this question. Right, let's use that here to answer this question. So at this point, we are looking at 1.7, and we are then saying, if you're looking at the ratio of hydrogen, the ratio of the mass of hydrogen to oxygen, which one therefore? Because you saw that the molecular mass of oxygen is 16, and the molecular mass of hydrogen is equal to what? It's 1. We saw that. It's 1 gram per mole, but this one is 16 grams per mole. Okay, this is 1 gram per mole. Take a look. Think about this. So now, if this is the case, which option therefore is going to be the correct one? Because now, if you're going to look at H2O, what do you think? 2 times 1 for hydrogen and for oxygen is HO is 16. And so this is the same as the ratio of 2 is to 16. If you simplify the ratio of 2 is to 16, what does it become? So you like divide by 2, you also divide by 2. So yeah, you divide by the smallest one, because the smallest number between 2 and 16 is the number 2. 2 is the smallest one. So divide by the smallest one. You divide each of these, dividing 2 by 2, dividing 16 by 2. So dividing 16 by 2, what do you get? You get 8. And therefore the correct answer is the letter C. The letter C in 1.7. So we're looking at the ratio of the mass of hydrogen to oxygen. It is the ratio 1:8. Any question? Who does not understand? If you don't understand, please ask. If you don't understand,
explain na.
happy. Okay, that's fine. Right. We looked at the periodic table, and the periodic table is clear about the fact that the molecular mass, which is the relative atomic mass of oxygen, it's 16, and the relative molecular mass of hydrogen is 1 gram per mole. So now we can see that in H2O has 2 hydrogen atoms. Right, so if you're going to write H2O, you really can see, therefore, you have 2 hydrogen atoms to 1 oxygen atom. And therefore, you just substitute 2 hydrogen atoms to 1 oxygen atom. You substitute, hydrogen has molecular mass 1, and oxygen has 16 from the periodic table of the elements. And therefore, you just divide by the smallest one to simplify the ratio. And dividing 2 by 2 gives us 1. Dividing 16 by 2 gives us 8. And therefore, the correct answer becomes the letter C. We chose the ratio of 1:8. Okay, we continue and look at the next question. 1 mole of H2SO4. H2SO4. What do you call the substance H2SO4? What is the chemical name of this? Anyone? What is the chemical name of this mammal? This is called sulfuric acid. Okay, sulfuric acid. Like HNO3, HNO3 is called nitric acid. Okay. These are strong acids. Okay, so if you speak of H2SO4, it is called a strong acid. Okay, there are those acids that are very strong. If you you are put in these acids, you don't survive. If they put you in a drum that is full of sulfuric acid, it's just going to consume you and finish you. And nitric acid is also a strong acid. And another popular strong acid is also called the hydrochloric acid. Hydrochloric acid. Okay, right. So yeah, 1 mole of H2SO4 contains what? 1 mole of H2SO4 contains 7 atoms, contains 1 molecule, contains 6,02 times 10 to the 23 molecules. It contains 42,14 times 10 to the 23 molecules. Yeah, anyone who thinks of the answer here? Right, anyone who thinks of the answer, what do you think? Okay, I'm just testing you, Paul. I'm just testing you on this one. So which one do you think is the correct answer in 1.8? In 1.8. Right, so we're speaking of 1 mole of that. Right, we're speaking of 1 mole of that. So at this point, there is something that you need to remember from grade 10, because you are a grade 10 learner. So there's something you need to remember from grade 10. And now the stuff you need to remember from grade 10 is very, very important for you. And now you need to be able to tell what the answer is to this question. Right, so now it is exactly what you call Avogadro's number. So 1 mole will therefore contain Avogadro's number. So this number here is a specific number, and it's not just a number, it is called Avogadro. Avogadro's number. Right, so this Avogadro's number is actually nothing other than it gives us the number of the molecules in 1 mole of a substance. So at this point, 1 mole of this acid will therefore contain 6,02 times 10 to the 23 molecules. And that is the correct answer. And that is the correct answer. And the rest are wrong. Next question. Let's look at 1.9. Just enjoying some multiple choice. Which one of the following in 1.9? Right. Which one of the following solutions will not form a precipitate if added to a solution of silver nitrate? Which one of the following solutions will not form a precipitate if added to a solution of silver nitrate? Which one? Right. Which one will not form precipitate if added to a solution of silver nitrate? Right, so obviously at this point, it is nothing other than another substance that is of the nitrate type, and therefore it is nothing other than what we call the magnesium nitrate. Magnesium nitrate. The rest of these salts will form precipitates. Okay, these are like salts, like your sodium chloride is table salt, is the salt you eat at home. Your magnesium bromide and your potassium iodide, these are all salts, and therefore the salts have a tendency to form precipitates. But obviously we're dealing with silver nitrate, and therefore silver nitrate contains a nitrate. Nitrate means NO3, and therefore at this point we are sure that magnesium nitrate will therefore not form a precipitate, because it is a friend of the nitrates. This is magnesium nitrate. We're putting silver nitrate in there, and these are all nitrates, and these are like cousins. They're good friends. They are all nitrates, and they not form precipitates. The rest of these salts, sodium chloride is table salt you eat at home that is used to season your food, and this one is a salt, and it actually forms a precipitate. The precipitate is the white stuff. Is the white stuff you put in the food. Okay, that is powdered there. That is crystallized. Okay, that is crystallized. Okay. The sphere in which minerals are found is known as which one? There is a sphere in which minerals are found. In which sphere are minerals found? Are they found in the atmosphere? Are they found in the biosphere? Are they found in the lithosphere? Are they found in the stratosphere? In which sphere are minerals found? Where do we find minerals? Anyone home? Where do we find minerals? Like gold, silver, platinum, this, that, you name it, diamond. Where do we find these minerals? We find them in what we call nothing other than in 1.10, we find them in the lithosphere. Find them in the lithosphere. We find them in the lithosphere. Right, so in the lithosphere, we find our minerals. And now these minerals are like gold, platinum, silver, and the rest of it. We find them in the lithosphere. These minerals are the ones we use to form cars, to make cars. The cars are metallic, and these metals, like we looked at steel, and we realized steel is an alloy, and steel is not a pure substance, for example. Okay, so yeah, just take note of those things. Let's move on. Question 2 now, it's about substances P, a substance P, a substance Q, a substance R. Okay, let's take a look at these. You have hydrogen, oxygen, sodium, chlorine, sulfur, iron. Take a look at this. The diagram below shows 3 different substances, P, Q, and R. Okay, define the term element. What is an element? What is an element? Okay, they're going to ask you this one in June. What is an element? What is an atom? What is a nucleus? What is an electron? What is a proton? They're going to ask you those things. But now here they're asking, what is an element? What is it? If someone asks you in chemistry, what is an element in chemistry? Okay, I'm going to define an element because I'm a chemistry person. So we're going to say an element is nothing other than a pure substance. A pure substance consisting of one type of atom. A pure substance consisting of one type of atom. So an element is a pure substance consisting of one type of atom. Like what? Like oxygen, like sodium, like hydrogen, like chlorine, sulfur, iron, you name it. These are elements. And those elements are found in the periodic table. The periodic table we're looking at a couple of seconds ago is nothing other than the periodic table of the elements we studied in chemistry. The next point, use the diagram and the key provided to answer the questions that follow. We're going to use this diagram and the key provided to answer the questions that follow. Okay, in 2.2, for example, in 2.2, we need to write down a letter that represents the following. Okay, we need to write down a letter that represents the following. Right, so there's something that we call a pure substance. Which letter? Is it the letter P? Letter substance P, substance Q, substance R? And now there are these black things, like there are these like white circles. These white circles that are like empty inside are hydrogen. Black, that is like black inside. The circle that's like full of black stuff is called oxygen. And this one, this circle that has like lines inside is called sodium. Okay. And then you have dot, 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 like this and that is chlorine. And then now you have this one that is like having some crosses inside is called sulfur. This one that is some lines that are like slanted, etc., is called iron. Okay, it's just the key for the key. Yeah, see, the examiner called it key. It's just the key to understand. They decided to just give us an example in the exam. Okay, just to create something in the exam for the grade 10 kids to get distinctions and get to university and do medicine and become medical doctors. And that is our dream. Our dream is to become medical doctors. Okay, so we define an element. Write down a letter that represents the following. A pure substance. Which one is a pure substance? Is it this one? P or Q or R? Which one is pure? I'm sure you did this in POR. Which one do you think is pure? Is it P or Q or R? Which one is pure? What do you think, Paul? Maybe you've never seen this
Second,
before. Yes, try. Is that Nombuso?
yes.
Okay, try Nombuso. Yes, please, you're welcome. Yeah.
I think it's substance Q.
Okay, that's fine. That's fine because we're learning here. And here we're not here to judge. Okay, now remember that a substance is pure if it's not mixed with anything, and it's like pure water does not have sugar, because once the water is having sugar, then it's not pure.
I
Because
see substance P.
well done, the substance P. Substance P is a typical example we want. So we are able to see that substance P is surely pure because there's only one type of a molecule, one type of an element, and you do not have like a combination of elements here. And now the rest of these are like mixed. They're like mixtures because you have different elements here. So that is something that, so substance P is correct. Substance P is a pure substance because it contains only an element of the same type. Next question. In 2.2, they asked the students to say, write down a letter that represents the following: a homogeneous mixture. So there's something called a homogeneous mixture. There's something called a heterogeneous mixture. What is a homogeneous mixture, Paul? Have you ever seen a homogeneous mixture? What does homo mean? Homo. What does homo mean? Okay, I'm still with Paul here. You are thinking Paul, right? Right, what does homo mean? Okay, for example, so which one is homogeneous? Which one is homogeneous? So homogeneous in the sense of what? Being uniform, but you look, it's homogeneous. Well, the word homo means same, but it must be a mixture. It must have like different elements, but for it to be a mixture must have different elements. So we expect a combination of things. So this piece out because it's not really a mixture. Mixture, you need to have different elements. So Q and you can be regarded, for instance, as a mixture, but is it homogeneous? So are these things exactly, for instance, the same? Are they the same? For instance, for example, in Q, you're able to see that this one is the same as this, and it's the same as that. But also this is the same as this, is the same as that. Okay. So as a consequence, then, we are able to see that a letter that represents a homogeneous mixture will be letter Q. It will be the letter Q. That represents a mixture. So you have different elements, but having different elements, and as a consequence, these different elements, you have some sort of molecules that are of the same type, like this, that, and that, this, that, and that, etc. And therefore, this qualifies to be a mixture. It qualifies to be a mixture. but that is homogeneous in the sense of having uniform molecules. Uniform molecules. Now, you need to think and understand what a mixture is. Because it is therefore a mixture because you have two. Like I made an example in, you put water. You put water and you add to water, you add sucrose. Sucrose, table sugar, or you can add like fructose. Okay, sucrose, table sugar, which is made from sugar cane. Okay, you put that in water, and therefore you have a mixture. So here you have two. You have this one, which is substance 1, and this one is substance 2. So in other words, now you have 2. So this one therefore qualifies to be a mixture because as long as these things, but this is the same as that. It's like H2O, because H2O, you really can actually be in a position to realize that you have 1 oxygen and your hydrogens there. Okay, so that will be, so this is an example, for instance, I mean, these can be like water. So you have water mixed with some sugar in there, something of that. That's just an example of the sugar. So obviously this is qualifies to be a homogeneous mixture. So it's a mixture that is obviously such that you have 2 substances and therefore it qualifies to be mixture. You have like water and sugar, so it's a mixture. Okay. Now in 2.2.3, there's something called a heterogeneous mixture. Heterogeneous mixture. Here, this one is not just mixing 2 things, but it's mixing too many. It's not just like water. It's not just like water plus sucrose, table sugar, and obviously you get a solution there. It's not. It's not that. It is heterogeneous. So obviously at this point, that's going to be clearly letter R. In letter R, we are combining like too many things. We have sulfur. We have iron. And then what else do you have, for example? And you continue here, for example, to have another sulfur. And you have another iron. And obviously you still have the sulfur there and iron. But obviously at this point, this gives us an example. So letter R gives us an example of what we call a heterogeneous mixture. A heterogeneous mixture. So you have, as we said, you have sulfur in particular here. Like what is evident is that we have sulfur mixed with iron. Right, we have sulfur mixed with iron, and that is the substance R. And sulfur mixed with iron qualifies to be a heterogeneous mixture. In this heterogeneous mixture, we actually are able to, why are we saying this? In a heterogeneous mixture, we are able to see still the reactants, if you like. Okay, so because in a heterogeneous mixture, you can mix, if you mix shoes, you mix shoes plus something, plus cups. Okay, you put shoes and cups together. This is an example of a heterogeneous mixture. Why is it a heterogeneous mixture? It is a heterogeneous mixture because if you mix shoes and cups, you still can be able to see that this one is a cup and this one is a shoe, a boot, whatever. Right, so because of this, you're able to see, okay, this one is a high heel shoe and this one is a cap. So this kind of a mixture is heterogeneous, where you still can see the things. Here, you are able to see the iron and the sulfur because they don't mix quite. And therefore, you are able to still see those substances there. Let's look at the next question. In 2.3, indicate whether the pure substance identified in question 2.1 in 2.2.1 is an element or a compound. Right, so let's look at that. Very interesting question. Indicate whether the substance identified in question 2.2.1 is an element or a compound. So in 2.2.1, we saw that it was P, and Numbers was able to see that P is the pure substance there. It is pure because you really can see that it is necessary. It's not a mixture. So it's the same kind of element that repeats. And now the question is, indicate whether the pure substance identified in question 2.2.1 is an element or a compound. Is this an element or a compound? That is what examiner is asking. This thing here.
It's an element.
Well done. It is an element. Very smart. It is an element. It is an element. So because it is an element, therefore, it is in particular the pure substance that to be identified there. And obviously, very well done. Can you give examples of the element that this can be? Okay, yeah. Still have the picture here. So obviously, it can be anything like H2 and because or like O2, etc. Okay. O2 is a very nice example of this because what is O2? Right, it can be any of these elements that are diatomic. Right, so the elements that are diatomic. So these diatomic elements are very, very important to us. In particular, are very important in this case. They are very important in this particular case. Right, so these diatomic elements are very interesting. As we said already, now, if you look at the diatomic, let me just write down because we're dealing with grade 10s here. So diatomic elements. Okay, Nambu, so we shall be meeting every single day this week. Right, so now the diatomic, now we learn, we can mention the seven diatomic elements. What are the 7 diatomic elements? It is hydrogen, oxygen, nitrogen. It is also fluorine. So this will be hydrogen, and this will be oxygen. This is nitrogen, and this one is, for example, fluorine. Fluorine is diatomic, and we also have your bromine, okay, which is Br2 is also diatomic, and then we also have our friend iodine. We also have our friend iodine as also diatomic. So yeah, so obviously we're just mentioning the 7 diatomic elements, and H2, O2, N2, F2, iodine, Br2. Okay, let us continue and answer this chemistry paper that had been written by the grade 10 learners a couple of years back. Now in 2.4, we're asking the question, which physical method would you use to separate substance Q into its components? Substance Q into its component. With which physical method would you use to separate substance Q? So to separate substance Q, what physical method would you use? So now at this point, we'd have to like separate water and salt. Yeah, in particular, this is like sodium and chlorine. So sodium and chlorine is this one, sodium chloride. So this is like salt. And it is combined with water. Okay, H2O. Okay, so we have H2O, which is water combined with salt. The question is, so yeah, the examiner was just trying to be creative. So the question is, how do you separate water and salt? If you take salt and you put into water and you stir everything in a dish, in a cup, you stir and allow the salt to dissolve in the water, how can you separate the two? What physical method do we use? What physical method do we use? Anyone? How do you separate a mixture of water and salt? How do you separate that? Right, you can use something we call in 2.4, use what you call evaporation. Okay, evaporation is also seen in the sea. If you go to the sea, and you're able to see that in the sea, the water is salty. If you go to the sea, if you go to Durban, you go to Cape Town, our Gauteng province is an inland province, but you see, if you go there, you will realize that, okay, the salt is left when the seawater evaporates, and people are able to harvest the salt. And this is the kind of salt that we put in food. And now this kind of salt it's a mixture. It occurs naturally because the sea water in the ocean is salty because it has natural salt in it. Okay, when it has natural salt in it, what do we do with the natural salt? We put in food. We eat this this salt. It is a spice. We spice our food with it. Okay, we season our food with it. So yeah, it's a seasoning substance. Let's go to the next question. So which physical method would you use to separate substance Q into its components? To separate substance Q into its components, we use evaporation. That is how we can remove water from the sea. From seawater. If you take seawater and you put it in the sun, it evaporates and the salt is going to be left there. Okay, some people go there sometimes. If you after swimming, you might find your body is having salt because that water there in the sea has salt in it. So if you go to the sea to swim, you might find your body with a bit of salt. When the water evaporates, because you go there, your body becomes wet because of the water. But when you are in the sun, especially in the summer days, now when the sun is hot, it removes, the water evaporates and you have salt on you, on your body. All right, in 2.5 now, write down the physical property upon which the separation techniques are based to separate the following substances into their individual components. Write down the physical property upon which the separation techniques are based to separate the following substances into their individual components. Okay, now write down the physical property upon which the separation techniques are based. Like if you want to separate substance R, what is the physical property upon which right, upon which the separation techniques. So if you want to separate the substances here, because we've already said that This one, this one, the black one is oxygen, and this is hydrogen. So oxygen and two hydrogens, we said already, is H2O. And this H2O, if you look at its molecular formula in organic chemistry, we shall get to that with the with Nombuso, and then yeah, it's gonna be water like that. So and then now you have the salt, which is our sodium chloride, and you'd have your sodium there. You'd have, so this is sort of a model. These are models we use in chemistry. Okay, but now if you write down the physical property upon which the separation techniques are based to separate the following substances into their individual components, what physical property it can be used to separate Q? Okay, and then so and then now also to separate R. Right, so now here we use the fact that in Q we use what you call the notion of the boiling points. We use what you call boiling points to separate these substances. Right, we use what you call the boiling points, and that is the physical property. We use what you call the boiling point to separate the substance Q. Right, so with using boiling points, we know therefore that water is able to boil because it's water. And therefore now you mix it with salt. And then now the water boils at, for instance, water boils at 100 degrees Celsius, but obviously because of temperature, water is able to evaporate when, because of its boiling point. And when water is exposed to temperature that is meets the sort of minimum, the water is able to change from its liquid state to the gaseous state. Okay, so we use boiling points. The notion of what you call a boiling point, because you now need to write down the physical property upon which the separation techniques are based to separate the following substances into their individual components. So to separate water and salt, we use the notion of what we call boiling point. That's called the physical property. And that is a separation technique. Why is it a separation technique? Because it is able to separate the water from the salts. So you can like break and have the water aside and the salt aside because of evaporation. Right, so the guys in the sea, they find themselves with salt on the face when the water evaporates because of the sun. Okay, the sun produces heat and radiation energy. Through the radiant energy and the radiant heat, the sun is the water evaporates from the skins of the people. Right, so if you look at R, what is the physical property to separate R? So now if you have, this one is iron and sulfur, what would you use to separate um iron and sulfur? What would you use there? What would you use to separate iron and sulfur? What physical property can you use there? To separate those, we use magnesium. We use magnesium. Right, so we use magnesium to separate this mixture of iron and sulfur. Right, so to separate the mixture of iron and sulfur, we use magnesium. So R would be that it is magnesium. And we use magnesium to separate the mixture of what? The mixture of this one, because this one is iron. You can see these things, they look like this in the key, okay? Because these round objects look like that and they're called iron, and these ones that have like crosses, sulfur. So you have iron and sulfur. Now in this kind of mixture, which is called the heterogeneous mixture, how would you separate? Use magnesium to separate sulfur and iron. Okay, next question. Right. In the next point, we're going to look at the graph. And graphs are very interesting in chemistry, and this graph is just no exception. So there's something called the vapor pressure. Question 3. The vapor pressure versus temperature. The vapor pressure versus temperature graph below was obtained for 4 unknown liquids, A, B, C, and D. Atmospheric pressure is measured as 101,3 kilopascals. So at this point, if then we have the given information, the graphical representation, and the graphical representation is about the vapor pressure versus temperature. Graph below was obtained for 4 unknown liquids. What do we have? The vapor pressure versus temperature. Okay, let us look at this. Let us look at these together. Let us look at these together. Right, so we have the following. Right, define the term boiling point. What does boiling point mean? What is the boiling point? What is it? They ask this even in matric. They ask this even in matric, Nombuso. So what is the boiling point? What kind of and a mammal is this? What kind of stuff is this? What is a boiling point? Okay, let me define a boiling point because I'm a chemistry student. As a chemistry person, as a chemist. Right, so the temperature. The temperature of the liquid. The temperature of the liquid at which the vapor pressure equals the, okay, we continue to define what you call boiling point. We continue to define what you call the temperature of the liquid at which the vapor pressure equals the external atmospheric pressure. Okay, now let's look at this. Atmospheric pressure. So the temperature of the liquid at which the vapor pressure equals the external atmospheric pressure. The temperature of the liquid at which the vapor pressure equals the external atmospheric pressure. That is called the boiling point of a given substance. Boiling point is, by definition, the temperature of the liquid at which the vapor pressure equals the external atmospheric pressure. So the temperature at which vapor pressure equals the external atmospheric pressure, then that is called the boiling point. So boiling point is to do with vapor pressure equals atmospheric pressure. Vapor pressure equals atmospheric pressure. That is called the boiling point of a substance. Next question. Right, in the next question, we're going to look at the information given in the graph to answer the questions that follow. Okay, here's the graph. And the graph is having A, B, C, D. Right, so now use the information given in the graph to answer the questions that follow. Write down the boiling point of liquid B. Write down the boiling point of liquid B. What is the boiling point of liquid B? What is the boiling point of liquid B? Let's look at these together. So we're looking at the 3.2.1, the boiling point of liquid B. Liquid B, you can see its graph is like this. And then now we are able to see that it is obviously an increasing graph. And the couple of things that we can see, like this one is 25. So 25, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So this is like 5, then 10, then 15, then 20, then 25. So it's in steps of 5. 1, 1, 2, 3, 4, 5. It's in steps of 5, this thing. So now the question becomes, what is the boiling point of liquid B? What is the boiling point of liquid B? So you need to look at this question very carefully and look at the vapor pressure. So we define the boiling point as the temperature of the liquid at which vapor pressure equals external atmospheric pressure. So this is the vapor pressure graph. Right, so the vapor pressure is there, and you can see that over there, and it is ongoing like that. So you can see that at this point, you add 5 to 75 and get an 80. So you get 80 here. Okay, when you get 80, now there's a point where the vapor pressure equals like the atmospheric pressure. So it is the vapor pressure we use. What is the vapor pressure here? Right. So at this point, we're able to see, therefore, that the vapor pressure is 80 because it's 75, and this is in steps of 5. So this is going to be exactly 80. So that at this point, we're able to see that the actual boiling point is 80 degrees Celsius. It is 80 degrees Celsius there. Next question. So make sure you understand how to read the vapor pressure graph because it's going to be there in your exam. It's going to be there in your exam. Okay, next question. Now we're looking at 3.2.2. 3.2.2. In 3.2.2, there's write down the liquid which remains when a liquid at 100. Yeah, write down the liquid which remains when a liquid at 115 degrees Celsius. Right. So we continue. Okay. We continue. Right. Okay, yeah. Write down the liquid which remains when a liquid at write down the liquid which remains a liquid which remains a liquid at 115 degrees Celsius. There is a liquid that remains, so even if you heat it, water does not remain a liquid at 100. At 100, water begins evaporating. But now, water boils. Water boils at 100 degrees. So that's what I'm trying to say there. So now, the liquid which remains a liquid at 115, which one is it? Which one is it? The liquid remains a liquid at 115. So you need to check. 115. Right. So if you check 115, so this is like 100, then you 105, you add 5, 110, 115. Okay. So this is like 5, like it will be 80, 85, 90, 95, 100. 105, 110, 115. Okay, something of that sort. Something of that sort there. Okay, so at this point, the question becomes, if you have about 115, which one then would remain and not be converted? And not be converted in 3.2.3. Okay, you need to look at that very carefully and reason. So if this is 105, 110, 115, and you are able to see that at about 115, let's just draw a vertical line there. 5, 10, 15, draw a vertical line. Vertical line, vertical line, vertical line, and see on average, this is what you're going to have. So as you look at these very carefully, what then do you see? Right, what then are you able to see there? 5, 10, 15. Okay, look at that very carefully and reason with us. Okay. So here you do 1, 2, 3, 4, 5. 1, 2, 3, 1, 2, 3, 4, 5. Okay, something on average there. Okay, right. So if you have that, the question then is, okay, you can see that these blocks are not very uniformly the same from the examiner. This is 1, 2, 3, 4, 5. Okay, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. Okay, yeah, it's fine, but just that it was cut. But yeah, there should be 5 there. It was just cut. Okay, it's pretty fine. Right. So, I mean, with this, then what then do you say? But also, there is a liquid which remains a liquid at 115 degrees in 3.2.2. Right. So in 3.2.2, you are able to see that at this point, if you look at 3.2.2 and you look at liquid D, this one here, A, B, C, D, liquid D, you're able to see that at 115 degrees Celsius, this liquid itself remains a liquid at 115 degrees Celsius. Right. It remains a liquid at 115 degrees. So now, if you look at the fact that why are we saying that? Because we are able to see that atmospheric pressure is actually 101 3 kilopascals. And we're able to see that at 115, liquid D, for example, remains a liquid at 115 degrees Celsius because of the fact that this graph intersects the atmospheric pressure graph, which is 101. So at 101.3, so 101.3 is above 100 because this is 100. And then there's 101, which is a little bit up there. But at this point, you're able to see that these are the vapor pressure values. But obviously, if I'm to remove this mark, right, we are able to see that there's a liquid which remains a liquid at 115, and it is certainly liquid D at 115 degrees Celsius. It remains a liquid because you have this is 115 degrees Celsius, and you have at this point approximately the atmospheric pressure of 101 there. Simultaneously, the vapor pressure is pretty much the same. It's pretty much the same, right? So it is necessarily that there. It is necessarily that liquid there. Okay, right. It is liquid D. So if you look at 3.2.3, a liquid which is most likely to be water, Liquid is most likely to be water. So which one would be water? It's most likely. So it's an estimate on average. Which one is likely to be water? Is it A, B, C, or D? Which one is most likely to be water here? Right, clearly it is this one that is such that the atmospheric pressure, so at 100 degrees Celsius, right, at 100 degrees Celsius, you're able to see therefore that this graph here meets the 101.3 kilopascals. And at this point, we know very well that the vapor pressure equals the atmospheric pressure, and at the point that the vapor pressure equals the atmospheric pressure, you have what we call the boiling point, and it is certainly C. It is certainly C. So in 3.2.3, it is C, and C is nothing other than the liquid that is most likely to be water, because it is at 100 degrees that you have that the vapor pressure is about the same as the atmospheric pressure. Okay, because that is how we define the boiling point. How did you define boiling point? Boiling point is the temperature of the liquid at which the vapor pressure equals the external atmospheric pressure. And therefore we continue. And therefore we continue. Right, so this one here, as we said already, it is water is our C. This one is likely to be our water, which boils, whose boiling point is 100 degrees Celsius, because water at 100 degrees Celsius, you have that the vapor pressure is actually equal to the atmospheric pressure. Okay, it's equal to the atmospheric pressure. Okay, so that is something that you need to take note of. Let's continue. Let's continue. Okay, now there's 3.3, and 3.3 is a very interesting one. Let's take a look at that. There's something called the phase changes in chemistry. State the phase change that takes place at the stage when the vapor pressure is equal to the atmospheric pressure. Okay, so what is this? What is the state change that occurs, that takes place at the stage when vapor pressure is equal to atmospheric pressure? Okay, we're looking at 3.3 right now. And now, when vapor pressure is equal to, when vapor pressure is equal to atmospheric pressure, when, like, let's look at water. Okay, because we know water much. We use water to bath and so on. We boil water most of the time to make tea and all that. So the state, the phase change that takes place at the stage when vapor pressure is equal to atmospheric pressure. With water, when vapor pressure is equal to atmospheric pressure, what is the state change that occurs there in 3.3? We know that in the case of water, when water starts boiling, there is something called the liquid changes. Liquid changes to gas. Liquid changes to gas. So now with water, when water is put there, when water, the temperature of water reaches 100 degrees Celsius. When it reaches 100 degrees Celsius, we know very well, the water starts going up, then begins to evaporate. And therefore, there's a phase change. The phase change, water changes from liquid to gas. Changes from liquid to gas. That is the phase change. So the answer to this question, stating the phase change, liquid changes to gas in 3.3. Let's look at 3.4. Let us look at 3.4. What happens to the temperature of a liquid during a phase change? right? Only increases, decreases, or remains the same. What happens to the temperature of a liquid during a phase change? Like in water, when the water changes to gas, what happens to the temperature of a liquid during a phase change?
Yeah,
Right.
decrease.
Okay, yeah, I know it's a bit tricky, this one. Um, so when water changes to gas, because you are boiling the water, and this water in the pot is becoming water vapor, we call that steam, and we can see the steam that is exiting the pot because the water is boiling. What happens to the temperature there of a liquid during a phase change? All right, so we're looking at the at that 1 to 3.4, and the truth is the correct answer would have to be that the temperature remains the same. Okay, because we're speaking about a phase change at the minute that the water is changing from liquid to gas, the temperature is still the same because the water is changing inside the pot. So if it's changing inside the pot, the temperature is still the same at the moment that it is changing, because at the instant, not when the water vapor is reaching the sky or is leaving the house, because you are cooking in the house and this water vapor is beginning to go out through the windows, or reaches your face, this steam. But what happens to the temperature of a liquid during a phase change in the pot? Because the phase change happens in the pot. In the pot, the temperature in the pot is the same. The examiner is trying to trick you here, because the students are going to think, when the water changes to water vapor, when the water changes to steam, then the steam is going to go to the atmosphere. And in the atmosphere, there's no pot, there's no heat, there's no stove, and everything is cold there. And the students are going to think that the higher you go, the colder it becomes. And it's going to make sense that the temperature decreases. But the examiner is trying to trick you, because remember, what happens to the temperature of a liquid during a phase change? This phase change is happening inside the pot. It's not happening in the air where the air is cold. It's happening inside the pot. Inside the pot, the temperature is the same. Temperature is the same. So the answer is, during a phase change, the phase change happens inside the pot, and the temperature is it's the same there. The temperature is exactly the same. We look at the next question. Okay, let's look at 3.5 now. Explain the answer to question 3.4. Explain the answer to question 3.4. That is the question 3.5, and you're asked to explain the answer to that question, and the explanation is as follows. Now, in 3.5, we say energy, right? We say energy is used to overcome. Energy is used to overcome the intermolecular forces. So energy is used to overcome the intermolecular forces. The intermolecular forces. So we are saying energy is used to overcome the intermolecular forces. Right. So, and the kind of energy is heat energy. It is heat energy. So the energy manifests as heat. And we're then saying, because they're saying, explain why this temperature remains the same inside the pot, the same pot that the water is beginning to change. There's a phase change. The water changes from one phase, like the liquid phase, to what you call the gaseous phase. Okay, when there's this kind of phase change, what do we say? Okay, yeah, at this point we know very well that the temperature there is the same inside the pot. It remains the same inside the pot. Okay, the examiner is trying to play tricks here. But now if they ask to say, explain the answer to question 3.4, explain why is the temperature the same? Because energy is used to overcome the intermolecular forces, and when the intermolecular forces are overcome, they're overcome inside the pot. Because now we need to explain why water changes to vapor, why water becomes steam, why water evaporates. Because energy is used to overcome intermolecular forces. That is why there is a phase change. The phase change is caused by the fact that energy is used to overcome the intermolecular forces. Okay, these are the things that you need to take note of. Okay, I want us to look at 3.6. Which liquid, is it A, B, C, or D, has the weakest intermolecular forces? Give a reason for your answer. Which one is the weakest one? Such that if you put a little bit of temperature, quickly, this is a gas. This begins to boil. Which one? Is it A, or B, or C, or D? So the boiling is going to be seen by the notion of what we call the vapor pressure is equal to the atmospheric pressure. Okay, so which one is gonna boil? Which one, according to the examiner? You see, the examiner is being tricky. He's saying weakest. How do you see the weakest intermolecular forces? The intermolecular forces are the forces that keep this substance together. And at this point, which one is having the weakest ones? So the weakest forces are going to be seen because of the immediate evaporation, immediate boiling. It's going to boil first. Which one is going to boil first? So you need to be able to analyze graphs, guys, because they're going to be there in the exam. So clearly we can see that it is the one that is going to boil first. And at this point, if you look at the temperatures, you draw this one. Okay. All right. And let us draw carefully. Okay, now if you had to draw, if you had to look at the point of intersection of the vapor pressure with the graph. Okay, because now the vapor pressure of 101 is like here, and then there is a vapor pressure here with the graph, and then this one, and this one. Which one, folks? Which one is the correct one? Okay. Right, so we're able to see that it is exactly A. A has the weakest intermolecular forces. Give a reason why A has the weakest molecular forces. Because it's gonna boil first. It has the lowest boiling point. It has the lowest boiling point. It is the lowest boiling point. It has the lowest boiling point. How do we see that has the lowest boiling point? We said that boiling point is the temperature at which vapor pressure is equal to the atmospheric pressure. And the atmospheric pressure is 101.3, and the vapor pressure equals 0. And obviously, you can see the equality first at A at the least amount of temperature. And the temperature is about 50 plus 5 degrees Celsius. It's about 55 degrees Celsius, which is the lowest. The lowest boiling point means the weakest forces. The weakest forces. The weakest forces. We continue. We continue. Next. 3.7. 3.7. In 3.7, the question is saying, what is the relationship between vapor pressure of the liquid and temperature? What is the relationship between vapor pressure of the liquid and temperature? right? So let us look at this one. What is the relationship between vapor pressure of the liquid and temperature? Let us answer this one. Okay, what is the answer to this question? So what is the relationship between vapor pressure of the liquid and temperature in 3.7? So in 3.7, we're going to say the vapor pressure increases. The vapor pressure increases with an increase. With an increase in temperature. The vapor pressure increases with an increase in temperature. So the vapor pressure increases with an increase in what? In temperature. Okay, so that's something that you need to take note of. So that the vapor pressure increases with an increase in temperature. So in 3.7, that is the answer. Or you can say, if you don't want to say that, I'm going to write in green, you can say that vapor pressure. So it is that one or this one. You can say vapor pressure. Vapor pressure is proportional. Is proportional to temperature. It is proportional to temperature. Vapor pressure is proportional to temperature. Because vapor pressure is proportional to temperature, in other words, when the vapor pressure increases, the temperature also increases. So vapor pressure increases with an increase in temperature, and that is the relationship between vapor pressure of the liquid and temperature. Okay, because if you look at the vapor pressure of the liquid and temperature, because if the graph is an increasing graph like this, so when the temperature increases, also the vapor pressure increases, and that is the relationship between the vapor pressure of the liquid and temperature. So vapor pressure is proportional to temperature. So now, or you can say vapor pressure increases with an increase in temperature, and that describes the relationship. Relationship means when this one increases, what happens to the other? When temperature increases, vapor pressure also increases, and that happens there. So when temperature goes up, when it increases, vapor pressure also increases. That is why this graph actually demonstrates that kind of a pattern there, which is an increasing function. It's said to be an increasing function or an increasing relation. An increasing relation. Next point. Okay, let's look at question 4. In question 4, I want to start the table below and answer the questions that follow. Right, there are a couple of elements here, or we can call them either it's an element or it's an ion. Okay, so the examiner is saying it can either be an element or an ion. Right, the number of protons are 11, 14, 16, and the number of neutrons here are 12, 16, 16, and the number of electrons are 11, 14, 18. Now, we answer the question. Define the term atomic number. What do you mean by atomic number? Who knows what atomic number is? Paul, what do you think the atomic number is before you sleep? Because I know that now you might be falling asleep. What do you think the atomic number
I
is?
can't see what atomic number.
Okay, that is fine. Remember that this lesson is recorded, so even if I break, the sound breaks, when I post the video on the group, on the WhatsApp group, the video is going to have quality sound because it is recording this, the sound at the source. This sound is recorded at the source where I am. So it's not going to break this sound, okay? But I want to here mention something about the number of, the number of protons in an atom. The number of protons in an atom of an element, right? Of an element. The number of protons in an atom of an element So the atomic number refers to the number of protons in an atom of an element. So the number of protons in an atom of an element, these protons are actually what we call the atomic number. By atomic number, we mean the number of protons of an element. Okay? So by an atomic number, we just look at the number of the protons in an atom. And if the protons are a given number, then we say that is the atomic number. Okay, let us look at the next question in 4.2. So atomic number is just the number of protons. That's all in an atom. So atomic number of protons. That's all. Now, if you look at 4.2 and want to write down the chemical symbol of an element Q using the notation AXZ notation, the AXZ notation, right? So write down the chemical symbol of element Q. Right, we want to write down the chemical symbol of element Q. What is the chemical symbol of element Q? Of element Q in 4.2.1. Right, let us write down the chemical symbol of element Q. Right, a couple of things that are very important. The number of the protons are what? 14. So you have 14 protons, the neutrons are 16, and the electrons are 14. So what is the chemical symbol of element Q? With these, with exactly these. So I would like us to discuss this. So if you look at the number of protons, 14. So let's go to the periodic table. So you need to look at the number of protons. The protons are 14 and the neutrons are 16 and the electrons are 14. So it is neutral. The protons and the electrons are the same number, but the neutrons are 16. Okay, so now let us go and look for an element with 14 protons, which is the atomic number. So let us go. I'm going to the periodic table now. We're going to see the periodic table here of the elements. We're going to see the periodic table of the elements. We're going to see the periodic table of the elements. We're going to see the periodic table of the elements. So now this is the periodic table of the elements that we study. Okay, if this is the periodic table of the elements, we want to know something. If we want to, okay, we look at the key and we're looking at the atomic number. Atomic number is what sits here. Like the atomic number of copper is 29. The atomic number, there's an element with atomic number 14. Which one has atomic number 14? So you must look and identify atomic number 14 and which one that is here. It is exactly this one here. And this one is called silicon. So you can see that it has a relative atomic mass of 28. So it's 14 silicon 28. Right, so it's 14 silicon 28. Right, so as a consequence, what we then are able to see is the following. Right, so it is silicon. So let us continue. So now we're going back. Right, so we're going back to be in a position to deal with that one. Right, we're gonna deal with it. Okay, look, I want us to deal with the chemistry. I want us to deal with the chemistry. Okay, we're gonna do lots of chemistry practice. We're gonna do lots of chemistry practice. We're gonna do lots of chemistry practice. Okay. Okay, so now let's write down the chemical symbol of element Q. Right, so we have seen that the element Q is silicon. Right, so we need to identify now the Z here, which is the number of the protons, and the protons are 14. So the Z is the number of protons. Okay, so the number of protons. So the protons are how many? The protons are 14. And then now we continue to look for the number of the up. Right, so we saw that it's silicon, it is 1428, which means that it is an atomic mass of that much. And now it is possible, therefore, to put this up here. And this can be seen as the atomic mass. Right. And because the examiner saw that the neutrons themselves are 16, we can be able to write that and say this is 14. And therefore, if you say then 14 and 14 plus 16, you get 30. So you can put 30 there. Right. So in other words, you are spoiled for choice, because now the protons are 14. You put the protons here. And then your neutrons are 16. And therefore, you can say 14 together with what? With 16. And that is going to give you 30. Or you can use the periodic table of the elements that says the atomic number, the atomic mass is 28, but the number of protons is 14. So you have 14 and 28 there. And this is silicon from the periodic table of the elements. Now, I want us to continue look at 4.2.2. 4.2.2. Element PQR. So this one we saw that it is silicon, and here you can put 30, 14. If you want to put the 30 and the 14, you can put right, okay, you can put 30 and 14. Or then you can put silicon, and then this is 28 together with 14. 28 together with 14. 22. So element PQR, that is an alkali metal. Okay, element PQR, that is an alkali metal. Okay, let's look at this one. So is it PQOR, that is an alkali metal? Let us look at that one. So in 4.2.2, we know that the element that is an alkali metal here, you need to look at that very carefully, is the element P. That is an alkali metal. And now the element P with 11 protons. So you can write the element R, it's enough. You can write the element P, so the P is an alkali metal. How do you see that? You must go to a periodic table. Okay, because you can see it has like 14 protons, and these protons show the atomic number. So you can go to the periodic table and then see the atomic number. 11. Check 11. Okay, so we're going to check 11. Right, so if you check very carefully, if you check now element 11, 11 is sodium. Right, so you can see that 11 is this one here, which is sodium. So if you have 11, it's sodium, and it is 23 here. Okay, so it's 11 sodium, 23. Now, atomic number is the number of the protons, and therefore there are 11 protons here, and this shows sodium. Let's go back. 11 sodium, 23. 11 sodium, 23. Let's go back. Right, so, okay, so yeah. 11 sodium. 11 sodium. Okay, yeah, we're back. So, okay, right. So, yeah, we're saying 11. So 11 is sodium. So you can either say PONA, and this Na stands for sodium. So write down the element. Is it PQR? That is an alkali metal. So it is now. This sodium is called an alkali metal from the periodic table. It's called an alkali metal. An alkali metal in the periodic table. Okay, so we continue. Now, the chemical symbol of R. What is the chemical symbol of R? The chemical symbol of R that is like 16 protons. Let's check. Atomic number 16. Atomic number 16. Oh, right. So let's check. Now, atomic number 16. Now you need to check. Right. So atomic number 16, it's sulfur. Atomic number 16 is sulfur. But now, okay, so it's 16 sulfur, 32 is the relative atomic mass. So 16 sulfur, 32. So let's check. Let's go back. Right. So we're able to therefore get here in 16 sulfur, 32. So something like that. So we're going to note that one here. So we come here. Right, so we saw that therefore you have 16 sulfur 32. But now if you look at these, you have that the electrons are 18. The protons are 16 and the electrons are 2 more, so they don't balance. So because they don't balance in 4.2.3, then you're going to say, now write down the chemical symbol. So the chemical symbol for 4.2.3, right, it's going to be sulfur 2 minus. Why? Because the protons are 16, but the electrons are 18, so they are 16 plus 2. So in other words, these are 16 and these electrons are 2 more, and therefore it's sulfur 2 minus. It's sulfur 2 minus. Okay, we look at the next one. Okay, here comes the next question. Here comes the next question. Element P reacts with oxygen to form the compound with chemical formula. This one. This element P, it reacts with oxygen to form the compound with the chemical formula. This one. Predict the chemical formula that element Rp in the periodic table will form when it reacts with oxygen. Predict the chemical formula that element rubidium in the periodic table will form when it reacts with oxygen. Right. So because obviously now let us look at rubidium in the periodic table, but also we saw that the element P is sodium. Okay. Right. So let's look at rubidium in the periodic table. Okay, I'm going to bring rubidium, Rb, check rubidium, Right, so if you look very carefully here and you want to identify rubidium, and rubidium is here. Okay, sodium and rubidium are in the same group. This is called group 1 of the periodic table. The halogens, we really can see them, the fluorine, chlorine, bromine, iodine, and astatine 0. Actually, what you can see sitting in group 7 of the periodic table, this is group 7. Okay. In group 6, you have oxygen, sulfur, selenium, and so on. Okay. And therefore, you also have in group 5 your nitrogen, your phosphorus, and so on. Now, in group 1, you have your hydrogen, lithium, sodium, potassium, rubidium. Okay. So now this one, if this one forms P2O, this rubidium is going to form Rb2O, and you go back because it has the same properties as sodium. Okay, so let's check this one. Let us check this one. Okay, let us check this one. Okay. This one is therefore going to form Rb2O. It's going to form Rb2O because we can see therefore that this and rubidium are actually in the same group of the periodic table, and therefore they share the same properties. They share pretty much the same chemical properties there. Okay, so this one here is going to be Rb2O. We continue in 4.3.2. Explain the answer to question 4.3.1. Why is it that the case? Why is that the case? Because Rb is in the same group. Is in the same group as P. Is in the same group as P. They are in the same group as P, or they're in the same group as sodium. Okay, they're in the same group as P, or you can say they're in the same group as sodium, and that is the reason why they would have the that particular formula there. Let's look at the next question. Let's look at the next question. So the next question is question 4.4. What is the trend in the ionization energy as you move from element P to element R? From element P to element R, and we are moving in this direction. What is the trend in the ionization energy? Write down only increases, decreases, or remains the same. Explain your answer. Write down only increases, decreases, or remains the same. Or yeah. Now let's look at that one. Let's look at that one. So in 4.4, what we're able to see, we saw that so I'm going to explain that. So in 4.4, we can see that the ionization energy surely increases, and we're going to explain why that is the case, because they said write down increases, so you can write increases. But you see, if you choose to write increases, and you explain from P, from P to R, the atomic radius. The atomic radius gets smaller. So from P to R, the atomic radius gets smaller. If you don't want to say that, or you can say the outer electrons, or you can say the outer electrons are doing what? They get closer. Get closer to the nucleus. Get closer to the nucleus. The outer electrons get closer to the nucleus. The outer electrons get closer to the nucleus. Right, so the attraction between the nucleus, the attraction between the nucleus and the outer nucleus and the outer electron gets stronger. Gets stronger. And because of that, therefore, more energy is needed. More energy is needed to remove the electrons. More energy is needed to remove the electrons. Okay, look. We'll continue. We continue. Okay, let's look at the attraction between the nucleus and the outer electron gets stronger. The attraction between the nucleus and the outer electron gets stronger. Okay. So more energy is needed to remove the electrons. That is also another way of further explaining that. Now, obviously, we are then saying, because the question is, what is the trend in the ionization energy as you move from element P to element R? Right only increases. We saw that increases from P to R. The atomic radius gets smaller. We're able to see, therefore, that the atomic radius gets smaller and smaller as you move from, obviously, because we know that we saw that this one is sodium, and we were able to see that R, for example, is the, right, we're able to see that R itself is S2 minus. Right, we're able to see that this one is S2 minus. And we're able to see that, for example, we're able to see that this one is silicon, Q. All right, we're able to see that this one is silicon. And obviously now, as a consequence, these patterns are very clear. And we're able to see that the outer electrons, we can say, get closer. Right, get closer to the nucleus. All right, so the outer electrons get closer to the nucleus. Okay, I need to write quite clearly here. So the outer electrons get closer to the nucleus. The attraction between the nucleus and the outer electron gets stronger. More energy is needed to remove the electrons. Right, so that is what we are able to see. The couple of things, obviously, that we're able to see, that, for instance, you really are able to see that there's an increase in the number of protons Okay, the increase in the number of protons has to do with the increase in the atomic number. Because see, the atomic number is 11, 14, 16. So the atomic number is increasing. 11, 14, 16. Okay, if the atomic number is increasing, that is the pattern we are seeing. And hence now, we're able to see, therefore, that there's an increase in the ionization energy as the reasons have been stated. Try to pay particular attention to the patterns stated there in this particular set of questions. Right, take note of that and make sure you understand that. Right, so let's continue. Let us continue. In 4.5, we're asking the question, how many electrons does an ion of element P have? Okay, we saw that element P is sodium. So, but how many electrons does it have? Right, so, and we'll continue to draw what we call the Aufbau diagram of this ion. So we are dealing with an ion of an element. So how would an ion look like? Because if sodium loses an electron, then it becomes Na plus. Okay. We saw that it has Na has 11 protons. Has 11 protons and is 11 electrons. If it loses one electron out of the 11, then that is the question asking, how many electrons does an ion of that have? So it would have 10 electrons. Okay, because it becomes Na plus, and Na plus means that it was like neutral before, but now it's becoming Na plus, meaning it has lost one electron. It loses an electron according to the reaction, right? So it becomes Na plus when it loses one electron. So Na becomes Na plus one electron. Okay, we're gonna get to more practice of these things. I want us to even have further discussions this week, more of this. So the idea of what we call the Aufbau diagrams of these ion is something that you need to learn. Let us discuss what we call the Aufbau diagram. Right, so we're going to have 2p, 2s, 1s. And we're going to have that the 2p has 3 cells like that. And this one is a single block or a single cell. And this one also has a single cell for the 1s. Now we note that we're dealing with a total of 10 electrons, and we need to put the electrons. This once we start with 1s, it can have a maximum of 2 electrons. So this one here, 2s, a maximum of 2. And then now we have 2, 4. You have 2, 4. And then we're left with 6 because there must be 10 in total. So the 2p now would therefore have, right, so you have those 1, 1, 1, and you feel like that. So 2, 4, 6, 8, 10. And this is called the Aufbau diagram. Okay, something that you need to learn, and we're going to discuss this. I'll have to test your understanding of this kind of a diagram. When orbitals of identical energy are available, the electrons are placed in individual orbitals before they are paired. Give the name of this rule. When orbitals of identical energy are available, electrons are placed in individual orbitals before they are paired. Give the name of this rule. That is called the Hans rule. Hans rule. That is the rule. Is called Hans rule. And Hans rule explains that when the orbitals of identical energy are available, the electrons are placed in individual orbitals before they're paired. Give the name of this rule. Is called Hans rule. Okay, yeah, this is enough for today, and we're gonna continue next time. We ended it at 4.6. Thanks a lot for joining us, and Paul, we're gonna discuss some further questions in our next meeting. Okay.